A group of scientists from France has presented a contact lens that allows one to see invisible infrared radiation without any additional devices. This became possible thanks to a physical effect known as upconversion, in which electromagnetic radiation of one frequency and wavelength is converted into electromagnetic radiation of another, higher frequency and shorter wavelength. For example, green light can be converted into blue, or infrared radiation into radiation that falls within the visible spectrum. As you have probably guessed, in today's video we will explore the physics of upconversion, examine how it was applied to create an infrared contact lens, and look into other useful applications of this technology. Let us recall the basic theory of resonant emission and absorption of light by atoms. An electron in an atom can occupy various energy levels, meaning it can have different kinetic energies and be located at different distances from the nucleus. If we provide the atom with a specific amount of energy sufficient to move the electron to another energy level, for instance by hitting the atom with a photon of that exact energy, the atom will absorb that photon, the electron will jump to a higher energy level, and then after a short while, it will return to its original level, emitting a photon, of course, with exactly the same energy as the one it previously absorbed. But what happens if, between absorbing the first photon and re-emitting it, the atom absorbs another photon with energy corresponding to a transition to a yet higher energy level? The atom will undergo the corresponding transition, and then during relaxation, it will emit a photon whose energy equals the sum of the two absorbed photons. That is, a photon with higher frequency and shorter wavelength. This is what upconversion is. The only thing left is to find atoms that have a suitable structure of energy levels, such that they feature transitions that can be triggered by infrared photons, producing a visible photon at the output. At the same time, we would very much prefer that the electron stays on the first step of the energy ladder a bit longer, to increase the chances that the atom will live long enough in the excited state to absorb the second photon. Such elements are already known. For example, erbium is often used, a rare earth metal belonging to the group of lanthanides. Erbium has many energy levels and sublevels, among which there are ones useful for upconversion. For instance, transitions from the ground state to the state labeled 4I11/2, and from there to the state 2H11/2 are commonly used. Both of these transitions are excited by infrared photons with a wavelength of 980 nanometers, while the transition from the level 2H11/2 to the ground state results in the release of a photon with energy of 2.4 electron volts, which corresponds to a wavelength of 500 nanometers, the wavelength of visible green light. And it would seem everything is simple. We place something saturated with erbium atoms in the path of the infrared radiation stream and enjoy successful upconversion. In practice, it turns out to be a bit more complicated. Erbium is quite reluctant to absorb infrared radiation with a wavelength of 980 nanometers. Erbium atoms absorb only a tiny fraction of the incoming stream of infrared photons, and the chance that such absorption will happen twice in a row during the 50 microseconds that erbium lives in the excited state 4I11/2 is nearly zero. A relatively good absorber of photons with a wavelength of 980 nanometers is a relative of erbium, ytterbium. The absorption-related quantity called the absorption cross-section is 100 times higher for ytterbium. Unfortunately, ytterbium does not have a suitable ladder of energy levels, meaning that while it can absorb a photon, it can only absorb one, and when it re-emits it, the photon remains in the infrared range, so no upconversion occurs. However, it turned out that the effect can be achieved by using erbium and ytterbium together in a pair. Ytterbium absorbs photons with a wavelength of 980 nanometers, and then transfers the absorbed energy to erbium via a process known as Förster resonance energy transfer, abbreviated as FRET. This process takes place when two atoms with similar energy transitions are located close to each other, and one of them is in an excited state. This is somewhat similar to the following. If you take two identical tuning forks, strike the first one, and bring the sounding fork close to the second one will also begin to resonate. Förster transfer, or FRET, is a purely quantum mechanical effect, and explaining its physics clearly is not very simple. Sometimes it is presented in a very simplified way, like this. Let us consider two atoms, ytterbium and erbium, located next to each other, with the ytterbium atom already in an excited state. Such an atom can be imagined as a dipole, creating an electric field directed from positive to negative, that is, from nucleus to electron, in our case, from left to right. This electric field acts on the erbium atom, attracting its nucleus and repelling its electron. However, after half a period of the electron's revolution, the direction of the dipole changes. The field is now directed from right to left, repelling the nucleus and attracting the electron. In this way, the dipole electric field kind of rocks the second atom, and with some probability, it will rock it enough to make it jump into an excited state. This intuitive explanation, as often happens in quantum mechanics, is completely incorrect. For instance, an electron in an atom does not orbit the nucleus at all. Moreover, Förster transfer does not actually occur between an atom in an excited state and one in the ground state. It takes place in the brief moment, lasting about 10 to the power of minus 13 seconds, when the first atom has already absorbed the photon but has not yet completed the transition to the excited state. We usually illustrate this process as an electron jump from one energy level to another. But in reality, from a quantum mechanical perspective, the situation is different. The electron is effectively split in two. One part is already on the higher energy level, while the other is still on the lower one. In quantum mechanics, this is described by saying that the electron is in a superposition of two states. It is written like this, where alpha and beta are the so-called state amplitudes. The square of each gives the probability of finding the electron in the ground or excited state. During the transition, alpha decreases, while beta increases, until alpha becomes 0 and beta becomes 1, and the transition is complete. But we are interested precisely in the moment when the transition is not yet complete, and the electron is in a superposition of two states. That is, if we look at our atom at one point in time, we will find the electron on the lower orbital, and if we look at another moment, on the upper one. Accordingly, its dipole moment will also be different in these cases, which means that from the point of view of the second atom, the dipole moment will oscillate. And if the dipole moment oscillates, then the electric field acting on the second atom will oscillate too. And in an oscillating electric field, the atom behaves the same way as it does at the front of an electromagnetic wave. That is, in the same way it does when interacting with a photon of the corresponding energy. It turns out that the frequency of the quantum oscillations of the field for the second atom exactly matches the energy difference between the ground and excited states of the first atom. I will not go into detail about how this is derived in quantum mechanics. It is done like this. You can pause the video and look closer. What matters is that an atom located near another atom undergoing a transition from the ground to the excited state is essentially in the same conditions as an atom struck by a photon whose energy matches the energy of the transition. And if the second atom also has an allowed energy transition with that same energy, it can undergo the transition, even though it never absorbed a real photon, but instead took the required energy from the first atom. That is the Förster transfer, and it is precisely thanks to it that the ytterbium-erbium pair, having matching transitions, can be used to upconvert infrared radiation into visible light. So, if we place a material containing erbium and ytterbium atoms in the path of an infrared radiation stream, upconversion can already begin on its own. The only essential condition is that the distance between the ytterbium and erbium atoms should be small enough, ideally around 1 nanometer. And indeed, it will start. However, the efficiency of such upconversion will not be very high. The process is simply too complex, and something can go wrong at nearly every step. First of all, ytterbium atoms do not absorb all infrared photons that pass by them. Second, after absorbing a photon and entering the excited state, a ytterbium atom does not always transfer its energy to an erbium atom via Förster transfer. It may just remain in the excited state for some time and then release the absorbed energy either by emitting the same infrared photon or even via a so-called non-radiative transition. For example, transferring the energy into the kinetic energy of thermal motion of the atoms in the crystal lattice. Third, even if the first act of energy transfer succeeds, the erbium atom at the first excited level must remain there long enough to receive a second portion of energy from ytterbium. again via Förster transfer. In general, the efficiency of upconversion in the case where two photons are converted into one is proportional to the photon flux density passing through the upconverting crystal. And the photon flux density is directly proportional to the square of the amplitude of the electromagnetic field oscillations at the wavefront. For streams of infrared radiation emitted by objects at room temperature, the efficiency of upconversion in a ytterbium-erbium pair amounts to mere hundredths of a percent, and the upconverted visible light will be far too weak to be detected by the human eye. In other words, upconversion will take place, but we will not be able to see the light produced in the process. Or more precisely, we will be able to, but only if we use a very powerful source of infrared radiation, such as an infrared diode, or better yet, an infrared laser. However, it is possible to increase the intensity of the radiation falling onto the upconverting crystal, not only by using a more powerful source, but also simply by concentrating the radiation from the same source into a small volume of space, similar to what a magnifying glass does. More advanced techniques can be applied using the so-called metamaterials. Ordinary materials consist of atoms and molecules arranged in a specific order by nature itself. Metamaterials are made up of microscopic structural units that we create artificially, and we also impose a specific geometric order on them artificially, which gives these materials very unusual properties. Metamaterials are a super interesting and super promising area of scientific research, holding the potential for truly astonishing results. So we will certainly return to this topic in future videos. Some of these metamaterials are excellent for improving the efficiency of upconversion. For example, one can use so-called plasmonic metamaterials, made of many metallic spheres with diameters of several tens of nanometers. These suspensions are capable of concentrating the light flux in the gaps between the spheres due to so-called plasmonic resonances. Here's how it works. Let us consider a light wave passing through a medium filled with such metallic nanoparticles. In the field of this wave, the electrons and ions that make up the metals begin to experience the electric field. The field pulls the ions in the direction of the wave's electric field vector and pushes the electrons in the opposite direction. The field acts equally on both electrons and ions, but since ions are thousands of times heavier than electrons, they can be considered practically stationary, and we analyze only the displacement of electrons. This creates an internal field within the sphere, which tries to pull them back, similar to how a stretched spring wants to return to its original shape. And if we suddenly switch off the external field, then, just like a released spring, the electrons in the sphere begin to oscillate around their equilibrium position with a natural frequency determined by the material properties of the spheres. So then, the key idea is to make the natural oscillation frequency of the electrons inside the metallic nanoparticle, those same plasmonic oscillations, match the frequency of the incoming radiation, thereby achieving resonance. In that case, the amplitude of the oscillations will be maximal. And what do all oscillating charged objects do? That's right, they emit electromagnetic waves with the same frequency as the frequency of their oscillations. In the case of plasmonic resonance, this frequency will match the frequency of the incoming radiation, and what's more, the phase of the plasmonic emission will be opposite to the phase of the incoming wave. This means the primary and secondary waves will cancel each other out. The metallic nanoparticles will strongly absorb the energy of the incoming wave, and the resulting electromagnetic field near them will drop sharply. But it gets even more interesting when we look at what happens in the space between the particles. There, an electromagnetic field will also arise between the displaced electrons of one nanoparticle and the stationary ions of another, which have been left without their electrons. This electric field will also oscillate at the same frequency as the incoming radiation. But in this case, its direction will match the direction of the original wave, which means it will reinforce it. As a result, the field is greatly weakened near the nanoparticles themselves, but becomes strongly enhanced in the gaps between them by tens or even hundreds of times. These are the so-called hot spots, and if we place upconverting nanoparticles in these hot spots, the efficiency of upconversion increases accordingly, by hundreds or even tens of thousands of times. Such an upconversion material, made up of two types of nanoparticles, metallic spheres to concentrate the field, and crystals containing ytterbium and erbium atoms to perform the actual upconversion, can achieve a conversion efficiency of infrared radiation into visible light of up to 10%. For an infrared contact lens, however, this method is not very suitable. Metallic spheres are opaque to electromagnetic radiation, so ordinary light passes poorly through such a lens. Moreover, due to the concentration of light, the original light paths are distorted. Effectively, you would just see a bright glowing spot, not an image of the infrared sources. That is why, in the research we are discussing today, field enhancement using metamaterials was not employed. Instead, they used pure upconversion by embedding numerous microscopic spheres of sodium yttrium fluoride into a transparent polymer lens. The crystal lattice of these particles was doped with erbium and ytterbium ions. Thanks to the transparency of sodium yttrium fluoride, visible light could pass through unobstructed, with a faint visible glow added to it, which was the result of the upconversion process. Thus, a person wearing such a lens can, in fact, see both in the normal visible spectrum and simultaneously in the infrared range. However, only strong sources of infrared radiation become visible. Natural thermal radiation, like in thermal imagers, cannot be seen using such a lens. And this is not only, and not even mainly, due to upconversion efficiency or the nominal power of the sources. Upconversion works with infrared wavelengths on the order of 1,000 nanometers. However, the human body, the bodies of other living organisms, and in general all objects with temperatures around tens of degrees Celsius emit radiation mainly at wavelengths on the order of tens of thousands of nanometers. And such long wavelength radiation simply cannot initiate upconversion in the ytterbium-erbium tandem. Upconverting lenses built using this technology cannot replace night vision devices. That said, they may still find their own areas of application. They could be used to see in the dark by illuminating the surroundings with infrared flashlights, invisible to anyone not wearing upconverting lenses. This could be quite useful for various special operations units or similar groups. In addition, one could use infrared signals for invisible communication or infrared beacons for identification and spatial orientation. So with some imagination, we can come up with quite a few use cases for this technology. Although, of course, it would be much cooler if upconversion allowed us to visualize ordinary thermal radiation from natural sources. But could we one day learn to do that with upconversion technology? Nothing can be completely ruled out, of course, but in my opinion, that is an extremely difficult challenge. The energy of photons with a wavelength around 10,000 nanometers is about 1/10 of an electron volt. First of all, we would need materials that have energy levels matching this energy gap. In principle, such processes are known. In atoms, for instance, one could use transitions not between different energy levels, but between fine or hyperfine splittings within the same energy level. Also, similar energies are characteristic of transitions between ground and excited vibrational or rotational energy states in molecules. These same energies are typical in semiconductors as well. Approximately this much energy is needed to free an electron from an atom and create an electron-hole pair, which can be viewed as a transition of the system to a higher energy state. So in theory, it is possible, but there is a huge gap between theory and practice. To put it plainly, upconversion using ytterbium and erbium converts two photons with energy around 1 electron volt into a single visible light photon with energy around 2 electron volts. And as we have seen, that is already a quite complex process. But if we are dealing with photons that each carry only about 1/10 of an electron volt, we would need 20 of them to make one visible photon. And with each of those 20 photons, something could go wrong. So the probability of successfully obtaining a visible photon becomes about 1 billion times lower. So even if someone theoretically figures out how to do something like this, in practice, it would almost certainly be an impossibly difficult task. It is far simpler to stop overcomplicating things and just use a regular thermal imager. Nevertheless, this does not mean that upconversion is a useless technology. On the contrary, it has many promising applications in a wide variety of fields. Upconversion processes can also be used to initiate photochemical reactions that would normally require ultraviolet radiation, but without actually using any ultraviolet light. Perhaps the most exciting application of upconversion lies in solar energy. Solar panels can effectively utilize only a portion of the solar spectrum in the range from 300 to 1,100 nanometers. As a result, a significant part of the sun's energy flow is essentially lost. By using upconversion, we can recover some of this energy from below the red limit of the photovoltaic effect, and thus increase the efficiency of solar panels by approximately 3 to 4%. That is a lot, considering that in solar energy, even a 1 to 2% increase in efficiency is already considered quite significant. By the way, I haven't forgotten that I promised my dear viewers a dedicated, in-depth video about solar panels and solar energy in general, and I will definitely make that video very soon. Among other things, we will talk there about upconversion and other promising methods for improving the efficiency of solar panels. So if you are interested in solar energy and energy technologies in general, be sure to subscribe to the channel so you don't miss anything interesting. And if you would like to support the development of the project, you can become a sponsor, right here on YouTube or on our Patreon and Boosty pages. A link to the latter should be appearing on your screens right now. That's all from me for today. All the best to you, dear friends, and see you again in our upcoming videos.